Give it a few minutes to let the rest arrive. While I get my water. I'm recording this lecture using case. Okay, well, let's begin. Well, you made it. You made it out of the woods, and now it's time to see applications. There are many, too many, that the application itself could be a class, like a separate semester. So far you have learned all the fundamentals of remote sensing with the example that we're running on Fridays. You're learning like how to develop complex or more complex projects than classification task or vegetation index. So these additional manipulation of the data allow us to calculate parameters or allow us to calculate characteristics of the surface that respond to a certain information needs. For example, here in Utah, we have been living under a 20-year, more or less, drought period. And how do we know that? How do we know that we live in drought? Well, mostly it's about the water stored in the reservoirs, water used by the different human activities, and in the case of the northern part of Utah is how much water reached the Great Salt Lake. So the drought is not only a climate issue, it also has a social component or a human component that we can see the effects. Less farmers producing water, calls to reduce water usage in urban areas, and effects on the ecosystems, natural ecosystems around the region. So when several voices arise regarding what should we do about water use in the state, one of the main or initial voices were, let's eliminate the alfalfa production of the state, out of the state. So no more alfalfa. And in a simple mindset, that seems to be a right direction to do. But looking into the details of how alfalfa production is ingrained in Utah society, we see that it's not an easy task. It's not an easy task just to call and say, let's change crops by tomorrow. There is a social, economical component that has to be answered to ensure that the results of changing a crop do not have worse consequences that is managing better the crop. Managing better the crop means understanding the water use, not only for alfalfa, but also for any other crop. We here, the northern part of Utah is one of the allocation where we produce potato seeds. This is a very valuable business. This is because the seed production has to demonstrate that the quality of the product is up to the standards, like free of viruses, let's say germination or transplanting success. The variety is adequate for the regions it's going to be planted. And across the state, we have other crops, like we have onions or fruit trees, and also we have hay production. So how do we, or the state agencies or the federal agencies can know, and society itself can know and understand better how water is managed across the state? And that takes us to that concept of water balance. How many of you have taken a hydrology class or a hydrology lecture? Okay. What is water balance? Okay. Water balance, in simple terms, it's all the inflows are equal to all the outflows plus minus a delta in storage. This is the simplest way, the most abstract way to represent water balance. Inflows, what we have in inflows in a basin scale? Precipitation, rainfall. Rainfall could be liquid or snow. Okay, so this is snow or precipitation. Anything else? Stream flow. The stream flow. Stream flow. Okay, that's our inflow. What's our outflow? What leaves the basin, or in any way? Evaporation. Okay, evaporation. Evaporation. And this is when we use the term evaporation, it's for open water, lakes, reservoirs. But there is another term that is more specific, is evapotranspiration. And this is for land surface areas. So that means forest areas, urban areas, agricultural areas. What else? We have here. Stream flow could be out, sorry. Yeah, here, right? Yeah, stream flow. Yeah. Leaving up, leaving out. And what is this one? What is the delta? What are the hydrological variables that represent the delta? Groundwater. One more. Lakes. Lakes, yeah, changes in lakes. And soil moisture. You might argue these two are in the soil component. Groundwater is for saturated soil, like all the empty voids in the soil are full of water. And soil moisture is the top layer where the water variation is significant. Groundwater changes more slowly, but so this is, in simple terms, how water changes conditions. So for any state agency, federal agency, as to understand is the sources of water that we have will dictate how much of these components happens and affect what is left at the end of the year. So one of the major components for us, and the topic of today, is this one. And let me tell you one interesting thing. You are living in a very extraordinary time in history. Oh, for real. You're living in a very unique moment, and you are at college just at the right time. Why? Because, well, all of this in the past was measured by gauge stations and visit to the sites and the data that we could collect to solve the water balance, to understand how water circulates through a basin, was very sparse, very limited, and we have to do educated guesses when we didn't have enough information. Nowadays, remote sensing can do rainfall. Remote sensing can do is what remote sensing can do is starting to do it. It is starting to do it and it's getting better. So pretty much we are getting closer and closer to estimate all the different components of the water balance with remote sensing. So today we're going to see one of the, I will say, the one that has been very critical for the entire process of for the water balance, which is evapotranspiration. And that's today's presentation. Okay, what do you understand by evapotranspiration? The water losses, right? So water cycle, you have seen this cartoon since kindergarten, right? The sun warms up surface water, which becomes vapor water, reaches a cold or cold enough, and in presence of orographic changes, orographic means changes in terrain, it cools down even further and it starts precipitating, which creates the stream flows, and we use that water, and some of that reach out again the open water. So evapotranspiration is going to be the sum of the transpiration of the plant plus the evaporation from the soil. Now, if the soil is wet for the same solar radiation conditions, we will have a higher evapotranspiration. If the soil is dry, despite we can be at mid-July, like high solar radiation, our ET is going to be slow. Okay, so this in the same case, if the soil has enough water in it, the plant will use this water to develop the biomass. And every leaf, as we learned in the remote sensing about transpiration, of vegetation, has a stomata, and this stomata will is part of the photosynthesis process. So more water, more biomass, more biomass, more stomata, more photosynthesis, so higher transpiration. So soil moisture will influence the development of the biomass, which in turn influence the transpiration and also the evaporation. So there is a relationship between how much water there is in the soil that will evaporate and how much water is in the soil that the plant will take advantage of to do the photosynthesis process. Now, why ET? Why we're starting with ET? Because knowing how much water natural environment uses, like forest areas or agriculture or the quad used to, it's important. Let's say the quad, how much water do you think it needs? Or how anybody can know, okay, I'm going to plan or create a new golf course in Utah, like 9 holes, drive and with sand traps and such. The first question is from where I'm going to get the water and how much water do I need? So that's ET. ET is that amount of water that will be needed for that specific plant under those specific climate conditions and soil. So ET allows us to understand how much water is used in agriculture in urban areas and natural areas. It allows us to assess the drought impact or how much reduction in crop production, or how many parks, or how green parks or parks in urban areas are handling the reduced irrigation. Water budget, this is water budget, to see how this inflow has been distributed along the system. Aquifer depletion, it allows us to see how much water is extracted from the ground to satisfy our human water needs, and monitoring crops and carbon budgets. Because we have biomass, plants, because all the plants will transform atmospheric CO2 into organic CO2. So that's the biomass. So when doing these studies of climate change, the additional CO2 being pushed by the fossil fuels burning, it motivates the plants to use more of that CO2. And in fact, we're seeing in some areas that they're greener than in past years due to the additional CO2. So to monitor how is going to be the overall impact of climate change, we have to keep track of how much the vegetation takes out from the atmosphere and convert it into organic carbon. Now, ET is a concept that is not new. The concept has existed for more than 50 years. And scientists all over the planet have tried to measure it in many different ways. The challenge is that it varies from place to place. And this is because it depends on the local climate conditions. It depends on the soil type, like the water properties of the soil water retention. It will depend on the variations in climate. For example, the total ET of turf grass in St. George for a year is different than the total ET of the same turf grass in Logan because the weather are just different. And the vegetation itself, plants use water in different ways. So what you're seeing here are maps of evapotranspiration. And these maps are showing different colors represented here by this scale in millimeters per day. It's not uniform. This is agricultural land, and we're seeing that there are spots that are using more water, others are using less water, or are using very little water. So it's not that we can say, oh, the average ET for Cache Valley is 5 millimeters per day, or 5 millimeters per day. This is another image. This is a river corridor, and we see vegetation will grow in certain areas in either sparsely or more dense conditions. And again, depending on their access to water, they will have a higher or lower ET. So how we solve that? How can we measure that? To measure ET, and this is, how many of you knows Larry Hibbs? Yes? Yeah, remember the professor that came early in this? He is an specialist on what we call it the eddy covariant systems, or in micrometeorology. Micrometeorology means the very local conditions that affects the distribution of this solar radiation into different components. Now, the instrumentation that he is well versed on is called the eddy covariant system, and it has a series of sensors. It has a sonic anemometer, a net radiation sensor. These instruments are different than a weather station, a typical weather station, in the sense that these instruments allow us to measure directly the water vapor, or this transformed liquid water from the soil and from the plant due to the solar radiation, meteorological conditions, the status of the plant, how much water is in the soil. It can capture at an extremely fast velocity. I think it's about 10 hertz. The sensor could at 10 hertz, or 10 times per second. It's measuring these the concentration of these water vapor molecules. This instrumentation is newer than this technology, lysimeters. Have you heard about lysimeters before? Lysimeters basically are a scale, a varied scale. It's what I mean is this is a box on which an area, let's say in this farm, was excavated carefully, removing layer by layer of soil. Okay, at the bottom of this excavation, there is plate, a scale, and on top of this, there is this box. It could be a concrete box, it could be another material box, and then the soil layers that we removed, we put it back in the same order, trying to replicate the natural conditions around it. Okay? It is provide energy, but the idea is to do a water balance, but in a box. Since you know the volume, okay, and the changes in water, let's say, if there is an irrigation or rainfall, my scale is going to increase the weight, right? Then, as the days pass and the plant starts using water, you see changes in the scale, start weighting less. So that changes in weight after the rainfall is ET. At the very bottom, it also has a drainage system that mimics the deep percolation of the water towards the aquifer. So I grew with this technology when I was a student like you. This is the technology that was available. So, but the limitation of this is that I can put only, these are very costly. Yeah.
Yeah, I was just gonna ask, so maybe this is insignificant, but like, as the plant grows, it seems like it would get heavier. So do you have to like account for like plant growth in the, like, in that, or?
Yes. Yes, that's a good question. How do we deal with weight, with changes on the crop?
So I take a dry weight the plant after
Like
collect
after it's
all the
grown?
plant matter.
After it grows, right?
Which is, I mean, if you dry down plant matter and weight, it's pretty insignificant. It's probably 5 grams, 10 grams. Yeah.
It's just, you know, negligible.
Maybe it's
They do it on
negligible.
a huge scale like that.
Yeah.
I'm sure they do measure it.
Yeah, but they do. They do. They take, probably what they do is because around the crop conditions are similar. Like from time to time, they take samples and they weigh that plant and say, okay, the average weight of the plants here at this moment in the year weights like this. So, but yeah, it's a good question. So it's a big scale. So we can solve it. Input minus output plus changes. So we can know how much water enters to the box, how much water is leaving. We can estimate this part. The limitation of this system is it's very costly, hard to change from site to site. There are people in the past who have dedicated their entire lives, their entire careers, just to run these systems. Okay? So nowadays, we have this. These are more portable. These are more, there can be implement, for example, how we implement lysimeter for forest areas. Hard to put a box and then transplant a tree in the box. But there are crazy people. There is one like that in California because they are waiting an almond tree, an entire almond tree. Crazy people. But yes, there is one. But imagine doing it in forest areas, anywhere in the state. Hard to do this. This one, the only thing that you need in these cases is height. You need to be higher than the tallest or the average height of the plants here. So these are becoming more popular. And there is nowadays a community of eddy-covariance researchers around the globe called FluxNet. And if micrometeorology is your is of your interest, I do recommend joining this page just for fun to know what's happening in the world of ET. Larry Hibbs is a member here, and I subscribe here to get feedback, progress, new studies on ground instrumentation to monitor ET. Utah State has lysimeters. There are where the Botanic Center, Caseville. We the plant climate, the plant soil and climate department has 2 or 3. I think they're being used to measure the water use of xeriscaping vegetation. So there is a professor Sun. a professor in the PhD department that is using them to monitor how much water these plants use over the season. So the lysimeters are not totally out, but they're used now where that instrumentation has been built. There is a newer technology coming in. This is, I would say, 5 to 10 years old. The lysimeters probably are a 50-year-old technology. The Evapotranspiration probably is a 30-year-old. So this is the newest one. It's called surface renewal. What it does, this type of technology, is take some components of the Evapotranspiration, but replace the most expensive one, which is the sonic anemometer. The sonic anemometer is like it's a sensor that has fingers, 3 fingers, like a better finger than mine. Okay, so that in this node is doing this 10 Hz measurement of water vapor, CO2 passing this, and is measuring the wind in the 3 directions: horizontal, crossing, and vertical. So that instrument is very expensive. It requires a lot of maintenance, like having an expert student or a personnel to go and clean it from time to time. But these ones require almost zero maintenance. They replace the sonic anemometer with this cage. It is giving good results. This is a company that came out of in California, called Thule, or Thule, and they are being promoted as a low-cost instrumentation that you can use to measure ET. Now, these are methods to measure, to get data, for true data. One characteristic of these methods is that they are just one point. They don't give you this spatial variability. Okay? They just give you where they are installed, they give you the value for that spot. You can argue that they represent the mean value for an area, and that's okay. They do. They represent a value for an area, but this area is not going to extend beyond, let's say, 200 meters, so, or 600 feet. So that's like the radius that they will represent, the maximum radius they will represent. So we need different tools to estimate ET. So I'm going to show you these 3 methods because there are no others. The first method is the one that I grew up with, is the crop coefficients. The second method is water balance. Water balance, we do it in all factors, from basins to sub-basins to even green urban areas or farms. Water balance, the concept of water balance is universal. The crop coefficients is a technique that allow us to do to grow the agricultural frontier. It allows us to allocate water in a best than not zero knowledge condition. Here is where we are right now, the energy balance. This is the methodology that is becoming the method to go to estimate ET. Okay, terminology. Okay, I work on ET, and ET terminology is very important. It's not the same. Okay, ET in general ET, the two letters, is a general term. There are specific conditions of ET. The second two are the potential ET or the theoretical maximum water use by a given plant, either turfgrass or alfalfa, under current meteorological conditions. This is what is reported by weather station. This is what, if you go to the Utah Climate Center, how many of you have used the Utah Climate Center for anything? Yes? Never? Okay. Utah Climate Center. Every state has a network of climate data. The Utah Ag Weather are the stations designed specifically for agriculture. Utah Trap are for tree crops, like fruit trees. But let's go to this one. Let's see. This is the state map of all these stations. We will choose one just to do a quick demo. Let's choose the Modena site. This is a weather station located just north of St. George. And let's see. Okay, there we go. We measure temperature, relative humidity, wind speed, rainfall, solar radiation, and here is our information about. Look that there is two letters here, ETO and ETR. What does it mean? ETO and ETR are theoretical formulations of how much water a specific type of plant will use under that under the current weather conditions. ETO is for turfgrass. Why turfgrass? Because we have turfgrass all over the planet. So we can all agree that, I mean, on a methodology that works for everywhere. From in Peru, we have green turfgrass areas. Here we have, and Russia also we have. So the ETR is recommended for agricultural crops, and that the crop of choice is alfalfa. Because again, alfalfa is one of those crops that is adopted all over the planet. Is the nutritious value, the easiness to grow it, and the lower care requirements than other crops make it a very suitable crop for cattle production. So alfalfa is that. So turfgrass and alfalfa exist all over the planet. And you can see the values are not the same. One is different than the other. It's about 20% the difference. And that's a conversion we manage when we transform one value to another. But we see that we get values of ETO at early scale based on the local weather conditions. Now, but that's for turfgrass and alfalfa. What about my corn, my onions, my cherries, my peaches, my almonds? What we need is another variable called ETA. This is actual or real. This is for my crop. I am growing hay, or this is forest ET. This is not turfgrass or alfalfa. This is the forest. So this is the value we need here. This ET that we have in the water balance is ETA, is the actual ET that we need. So these two are approximations to theoretical crops, but what we need is this value. How we arrive then from these two to ET? Well, there is a very simple concept based on basic algebra. The basic algebra is going to say, or this is the assumption, ETA it's in function of ETR. Let's choose ETR for now. Okay, we're going to do this assumption. We're going to say then F is linear. This is our second assumption. So we're going to say that ETA is equal to a factor called KC times ETR. We're going to say the theoretical multiplied by a factor gives me the actual. This is the crop coefficient. Okay, so what we're going to say is for a season, I might have the ETR and with the lysimeter, I measure this. With the weather station, I measure this. So I'm going to run experiments, and if this is ETR, and this is ETA, I can calculate KC by just dividing these two values. So I have this from the lysimeter of the eddy covariance, I have this from the weather station, I can calculate KC's values for the entire season. That factor tends to go from 0 to 1. So we will see a bit more in detail. And there is now KC is, let's say, is an approximation, and it's an average over many seasons. So this experiment with the lysimeter and the eddy covariance and the lysimeter and the weather station is done for many years, like 5 years. The average of those KC curves of the 5 years, it's what is we call it KC. So we remove, like, this year was slightly colder, next year is slightly drier. We try to average those differences per year when we take the average of KC. If it's only 1 year, we don't call it KC. We call it ET fraction. It's the same mathematics as the KC, but is what you're measuring in 1 single year. It's not an average. Okay. Because ETR or ETO is a model, is a mathematical model, how many equations are there for this calculation? More than 50. There are many and many, and every 3 to 5 years, a correction or an improvement of the previous models appear. And Utah Division Water Rights used to use a Presley-Taylor equation, a very old and currently not in use anymore, but that was the official methodology to calculate water rights. But nowadays, and in other locations like in Peru, most of the time you cannot put a well-instrumented weather station, so you put the minimal instruments, solar radiation and air temperature sensors. And for that, a USU professor, that you probably never heard of him, he was George Hargraves, developed a methodology that was really, really good, really, really good. So when you had only limited data, Hargraves, but nowadays, technology has become cheap. Campbell Scientific has and other companies like that have lowered the prices of instruments. So across the US, we use the Penman-Monti equations. That's for calculation of ETR or ETO. This is a formula that you don't need to memorize, but if you have taken a hydrology class, you have seen it, and some professors ask the students to derive this equation, especially if you are a grad student, because this comes from the energy balance with simplifications. But we know enough about this equation that with the data from the instruments, we immediately calculate this value. So there are no doubts about those values. So we're getting from the Utah Climate Center this data. ETR, ETO, but the Climate Center is not telling you, use this one or use this one. It's telling you, you choose. So it's up to us to decide which one to use. So crop coefficients is what I was explaining, is we have the climate and we have our grass. If we have that coefficient factors, we approximate the crop, and we can add additional coefficients to the KC to represent, for example, the variety. I'm using alfalfa variety that is resistant to drought, or a core variety that is resistant to a given insect. So I can add an additional coefficient to further adjust the use of water. So that it's harder to estimate the second one, but for the crop coefficient, we already have tables and books. And this is the book under I studied my undergrad as an irrigation engineer. The FAO 56 paper is by a professor, Richard Allen, an ex-USU professor, now he's in Idaho, which says early in the season, that KC value is going to be low. After, once the vegetation start flowering, the KC is going to be maximum. And then when it's ready to harvest, it's going to decline. So how much time each growing period lasts, and what is the assigned KC for these crop stages is described in tables. Pretty much all crops produced in the planet are here. So we can approximate how much water corn uses in Logan versus California versus Arizona. But the crop coefficients are going to be kind of similar. So we have the crop coefficient, we multiply it by the ETO, and then we have our reference ET versus our local or crop ET calculation. Simple methodology, it helped a lot of agricultural projects, to expand, to include new areas for production, because now we have a good approximation of how much water I need for a green, for a new golf course, for alfalfa, for producing more corn. And now the interesting thing, how we relate these to remote sensing. Well, it happens, okay? It happens that we found something very interesting, very. Do you remember NDVI? Your favorite index, right? Yes, your favorite index. So it happens that the KC is approximated 1.1 times it seems that there is a magic equation there. If you're using Landsat, MODIS, this is a very crude but simple approximation of the KC. So if you have a value of ETO or ETR and you calculate the KC, you just multiply the image and you get a map of ET. Fun? Fun. Okay, so this is a methodology. So what in California, what they have done is, okay, let's say we're going to calculate for almonds. So they figured out a slightly different value. A value almond factor times NDVI. Or let's say vineyards, also they have another factor times NDVI. So California, the state of California, uses this methodology to map their crops. They refine this value depending on the crop. So they have edicovariance towers. Over years, they have collected enough data to derive the crop coefficient, and they found that there is just this constant value is slightly different per crop. So they are refining it a bit more, but this is the general equation. So with that, they are estimating how much water, or the division water rights is estimating how much water the crops are using in California. So that's what they do. NDVI multiplied by a factor, that's your KC. Fun, huh? The second method is the water balance. This is a much harder method, and one that could get a bit more of help from the remote sensing part, because to solve it, while we can use the KC from NDVI, we also need to we need to track the irrigation amount, rainfall, changes in soil moisture, if there is runoff, or deep percolation. And installing sensors is not fun, especially if the root of the root zone, or the depth at which the roots grow goes up to 2 meters, like 6 feet or deeper. And doing with enough repetitions, it's hard. Soil moisture data looks like this. This is hourly or every 15 minutes data. We can see these spikes, and those are rainfall, the initial spike. The second part of the spike is the water reduction. So is that ET? Sort of. When irrigation and rainfall happens, like heavy irrigation, soil moisture will increase, of course, and from that, it'll start receding. This rapid receding is due to a major factor. The water is moving deeper. So at every moment, ET is happening. So we have at this period two forces, ET and deep percolation. But because of the volume of water is large, deep percolation is a stronger force until we see this change in the slope. Around here, all the changes in soil moisture are due by ET. The deep percolation phase has stopped. So we have from the irrigation, we have this period where deep percolation is stronger. After certain time, it could be 1 or 2 days, these variations in soil moisture, this decline in soil moisture is ET. So trying to do that, trying to do like taking difference of soil moisture values gives you data, but it can lead you to very erroneous data. Some locations, this is eddy covariance data versus try to estimate ET from soil moisture. We have gaps for the irrigation days. We don't know when that deep percolation phase ends. So hard to track, and is not recommended to use soil moisture for daily estimation of ET, more for seasonal, probably monthly scale, but not finer than that. There are other methodologies that I've never used it, but I've read and I found good information about it. Is called Hydrus. This is a numerical model that will model the water movement in the soil as irrigation or precipitation happens. Will apply soil water movement theory to estimate how much water goes into deep percolation or runoff and such. So I believe there is a professor on the PSC that works on hydros, right?
Scott Jones.
Scott Jones. There is another one. Yeah. But yeah, this is something that can be used, but you need a very expert people and very detailed information to run it. So it's more like for academic, scientific work. Okay, here we are. Energy balance, your favorite topic, because everything that we have studied relates to the solar radiation, right? So energy balance, what it's going to do is going to take that energy coming from the sun, part of it gets absorbed by the atmosphere, and some of warm up the energy, warm up the molecules of air, and then they start emitting. So we do a initial balancing of the solar radiation reaching the Earth surface. We call it that net radiation. That net radiation, now we're going to divide it into 3 components. Net radiation is going to warm up the soil. So when you touch soil in the morning and then at midday, it's warmer, right? That change in temperature is because energy has been absorbed by the soil. Okay. H is what we call it the sensible heat flux. Air temperature in the morning, if you go out today in the morning at 7 in the morning, it's cold. You go at midday, say, okay, I can handle it, right? It's warmer. The air temperature has increased. That increase in temperature means the air has absorbed energy. That is H. So from that net radiation, we have to discount what the ground needed to warm up, what the air needed to warm up. Okay, and because it's a balance, the what is left is ET. So if we are able to calculate net radiation, ground heat flux, and sensible heat flux, we can calculate ET. That's the premise of energy balance evapotranspiration. And we have become really good at it. Really, really good. So you live in an age where this type of calculations can be done with weather satellites, with MODIS. This is with the GO satellite. This is MODIS. This is MODIS, Landsat, and drones. The same concept in all of them is the same. Is calculation of net radiation, ground heat flux, sensible heat flux, we call it H, and the latent heat flux is evapotranspiration. So all of this nowadays is possible. So we're going to see an example of that. Let's see if we have enough time. This is how we have been using Landsat, right? There are different algorithms these days for the calculation, but this is how it looks like on agricultural land. We'll see high levels of ET in fallow areas. We'll see a very low amount of ET happening. What are the methods? There are many. This is a sample of the ones that are the most used in the US. Okay. The most popular, and I entered to the remote sensing realm because of this, is the metric model. It is the one that has been adopted by the different states in the western side of the US. Then is the CIBAL that comes from the Netherlands. It's a really good model. This is the father of metric. CBOB is from the Geological Survey. They also develop a methodology. Oh, by the way, all of them calculate net radiation, GH, but how they calculate it is different in each model. So they do a different approximation of those, of the values. The one that I use for research on drones is this one, the Alexi Disalexi. This is probably the most sophisticated of all of them. It's one of the sophisticated in the sense that describes it. This three on top makes certain assumptions. This one is the one that does the less assumptions. Still, it approximates things, but it does less assumptions than the others. This is the NDVI. Remember, NDVI times 1.1. This is the California method. It's called the SIMS. And NASA also developed their own method. They say, yeah, we're NASA. We're going to develop our own method. So they call it the JPL Presley-Taylor model. So now, where I can get ET? This is me. This is my research. I fly drones for a living and not for fun, but this is, if I have red, green, blue, seeing Landsat, near infrared, I can have a map of elevation to know how tall are the trees, and a map of temperature plus weather station data, ET. This nowadays is trivial. It can be calculated. In summer, we are planning to teach a 10-day flash course on how to do this with drones this summer. So we'll be posting around when this happens. But yeah, but this nowadays is possible to calculate ET, and while in Landsat is 30 meters or MODIS is half a kilometer, in this one is the pixel size is a 3. Every pixel here represents a 3. All right, so you might be too young to understand this reference, but if you understand it, you are too old to understand this reference. So let's see a true example of ET. There is nowadays, this platform is called OpenETData.org. It's free. So let's go there. ET data. OpenET, explore data. This is a project sponsored by NASA, Google, many organizations. USU is part of them. And this is a map of ET for the entire 2022 across the Western US. The resolution is Landsat resolution. Now you can see here from 0 to 47 inches. But if you are like me, you change it to millimeters and is 1200 millimeters. We want cities. Yes, we want cities. So bluish, highest use, yellowish, lower use of ET. And look, the most water is used around the Wasatch Mountain range. San George and Modena use the less water. But the thing is that we can go to any location we want.
The 1200 millimeters per time.
Per year.
Year.
Yes. So this is Logan. Okay, I don't know where I am because this is. Okay, where are we? Okay, this is the first dam. This is the water level. Oh, here is the quad. I want to know how much water the quad uses. Okay, where is my zoom in? Okay. This is the monthly ET from the 17 till this year. It's not every year the quad has used the same amount of water. But we see that in recent years has been using more and more in the summer period. Now, what you're being shown here is a weighted average of the 6 different ET models. You can look at the individual models here. Every model doesn't give you the same value. Remember, internally, they do their own approximations. So when they do that, their approximation might be adequate or not for that location. So what OpenET promotes is, okay, look, we know there are some that will give you higher values, medium, and some that will give you lower values. So we're going to give you a weighted average. So that represent where the models, most of the models are arriving at, not the extremes. So if you see the black dot is around here between these two. This is discarded and these two are discarded. I can see the range of the maximum and the minimum values for every month. So this is sort of my uncertainty for everybody. So this is what you're looking at. This is monthly data. Okay, that can help me to compare month to month, year to year. What about if I need daily? This is 2022. And you can see that this is ETA. You can see in winter months, we have in some days, we might have reached 1 millimeter, but then it increases, goes up and down with the weather, and then goes dormant again. This data is downloadable. You can get the daily data, you can get the monthly data, or you can see also the cumulative data, where you see how every year compares to each other in terms of total water. Okay, that's fun for that. What about agriculture or natural areas? Well, let's go to natural areas. Let's go. You see in the mountains, we have two valleys. This is the first dam, and around here, this is the Logan Canyon. This is the south slope, this is the north slope of the mountain. Where scale says this part has higher ET than this one. So due to the geological formations, we can see variability in ET. There is another way to see this data, and this is mostly for fields. They have taken all the GIS boundaries of every state. They are doing the average for every polygon. So this is the average for that polygon that I selected. I can get also the cumulative. What about open water? What about the Great Salt Lake? Could I get some data there? I could do this. Draw a custom area. I'm going to draw a rectangle. I need to make it smaller. This is water evaporation. So OpenET is a massive, massive project. And what the effort is becoming nowadays for OpenET is validation. The state of Utah is putting eddy covariance across the state. Larry Hibbs and the Bureau of Reclamation have been monitoring for more than 5 years, six stations across the different states. And so what we are doing these days is to ensure that this value is that value. So this comparison between what the OpenET is reporting versus the ground instrumentation can provide. That's the effort that the community is doing. So nowadays, if you are doing studies on OpenET or water balance, this is a source that you can use now. So it can be used for urban areas, can be used for natural areas, open water areas. There are no restrictions on the data. As we keep validating this model, also always use with caution. And OpenET, the team of OpenET is always open to questions like, did you have a report where you did that initial validation of your data? They have a report. They every 2 years, twice per year, like in February and then in September, internally they are improving the algorithms. Like the creator of every model of ET is saying, okay, I found that I can improve my equation by introducing this factor. They test it internally, and then in February, we get an update of the entire archive of OpenET. So it's always improving. So at some point, we will see that many of you will be using this data as part of different courses on campus. Okay, I think we have talked a lot about ET, but I didn't give you a chance to ask any questions. No questions? All right. OpenET is free. Open an account, even just for fun, and read about it. Read or use it, explore areas. If you have a relative or a friend that has a farm, check how their farm is doing in terms of water use. Or if you are interested, let's say in the bird refuge habitat, you can click in there and check how much water that region has been using. So use water around, or compare how much water Colorado versus California uses. So the database is yours. Okay. Other than that, thank you for your time, and I'll see you tomorrow, right? Don't forget to bring your questions. We want to address any restriction you have in your term project. Thank you very much.